Yes, you are.
Okay, thank you. So, our next session will be taken by Dr. Arnab Sinha. Dr. Arnab Sinha is a senior manager of applied science at Amazon, leading global teams that design, evaluate, and scale machine learning and econometric models powering the featured, offered, and product ranking systems across more than 20 countries. He has more than 14 years of industrial experience, including over 8 years of expertise in large scale experimentation, causal inference, and AI driven optimization, with prior experience at Microsoft Research, where he co founded the Microsoft Academic Graph and earned multiple patents. Dr. Sinha holds a PhD in electrical engineering from Princeton University and dual degree in computer science and engineering from IIT Kharagpur. Passionate about teaching and mentorship, he frequently delivered talks and tutorials bridging advanced science with practical, customer focused innovations. The work Dr. Sinha will be discussing today is jointly authored by Dr. Tanmoy Das. Dr. Tanmoy Das is a senior applied scientist working at Amazon since 2019, based out of Seattle. His research interests include causal inference statistics, recommendation systems, and marketing measurements. Prior to Amazon, Dr. Das earned his PhD from Ohio State University in and Master of Science from IIT Madras in the year of 2012, both in computer science and engineering. Dr. Das worked at Microsoft Hyderabad in Windows networking team between 2012 and 2014. I would like to invite Dr. Sinha and Dr. Das.
Thank you. Am I audible?
Yes, yes, you are audible.
Okay. Okay. Share my screen. A bit new to using Teams, so that's why.
No issues, you take your time.
Yeah. Okay. Let me see. Is my screen audible? Sorry, in my screen visible now? I'm sharing my check.
Yes, 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 your screen is visible.
Okay. Okay. Let's get started. Thank you, Dr. Bandyopadhyay, for inviting us to this event. I'm Arnav Sinha. I work with Dr. Tanmay Das, who is also present here. And today we will talk about a real-world application in artificial intelligence and its evaluation using techniques from econometrics and advanced statistics. By the end of this talk, you should have a high-level idea of how to use explore exploit algorithm to enhance a specific shopping experience and how to design and evaluate A/B experiments to evaluate such an experience. These methods are industry standards. However, by no means we claim anything about whether these methods are actually used in production in Amazon. Okay. So we start with a typical e-commerce website. This particular specific one is taken from Walmart, but you can imagine pretty much in any e-commerce website, you typically have a page like this, which is called the product detail page, which contains a plethora of information about the products, including both textual and non-textual. Information such as the product images and videos, the product description, price, the delivery promise, etc. Now, the question that we are raising here is that what is the optimal way to display all of this information? Because as you can imagine, that is sometimes it may cause some kind of cognitive overload. In this particular talk, we will focus on reordering the media contents, which essentially translates to the images, videos. Nowadays, you also have those 360-degree spinning contents. It can be sometimes like influencer created images or videos. It can be brand, we call it the A plus contents, basically the brand burnishing content, etc. The question before we go into the ordering, the question I'd like to raise is like, why does media content display order matter? The goal for the media content display is that we want to show the customer the most relevant media contents upfront that help in their shopping journey. Now, if you think about your own shopping journey, when you're beginning to look at a particular product, you can imagine that that certain type of media contents are probably more important than others. Now, let me first give some examples of what kind of media contents are typically available. There can be, I can give you three examples. Let's say the first primary image, which is generally in this particular example, the first image is that, which generally comes in a clean white background, which provides a first impression, which reduces uncertainty and improves trust and enable quick evaluation. Then there are like some lifestyle images. In this case, you can think of like maybe the third image in the first series of images. So they help customer imagine the usage, communicate the scale better, and also trigger emotional resonance. And then the other type can be, for example, the one that I have put a box around, which is called as known as the dimension images or infographics. They educate the customers quickly, they summarize the key facts, and also increase trust. So you can see that there are different kinds of media contents that are present. And generally speaking, at the beginning of your shopping journey, you generally look at or you're trying to evaluate if this is the right product fit for my needs. And generally, we start with a primary image, maybe a lifestyle image, etc. But as you kind of assure yourself that this is the right product for myself, at that point in time, you're looking to learn more about its maybe dimensions, maybe some other infographics, maybe the key ingredients, if it's a food material, etc. So as you can see that in the beginning of the shopping journey, the product dimension is less relevant. However, towards when you are almost making the purchase decision, at that point in time, the product dimensions make more relevance. So we can understand that this display order should be dynamic given certain features, and we will talk about what kind of features they are. But definitely, shopping journey is one of them. Another question is the to order or not to order this media content. So let's take this coffee maker. So for this specific coffee maker example, we know that we have about 12 images and perhaps one video. Now there are two important questions. What is the optimal display order? And second, how do you know that this is optimal? And this talk essentially is divided into this, just trying to answer these two questions into two parts. So how do you determine this optimal ordering? So first of all, what factors should determine this order? It can be classified into three different groups. The first one is the customer preference. Like some customers perhaps likes the videos more than images and vice versa. The stage in the shopping journey, as I discussed, in the beginning, you're trying to evaluate fit. But as you have already making your mind, that is, we call it the close to the add to cart action. It can be also related to the product characteristics. For example, in electronics, you probably want to learn about some of the configurations. For example, if you're looking to buy a router, you probably want to know like how much gigahertz it is compliant with, or if it's compliant with some other technical characteristics. If it's apparel, you probably want to take maybe you want to probably learn about its size and other factors. Now, what are the possible approaches of solving this problem? So, of course, if you think about it, one way can be like offline, like classical machine learning application, where you kind of train the model offline and then you deploy. But there are a couple of problems. The first problem is that the cold start problem. Uh, we call it, so for example, let's say you want to onboard a new media type or new media content. It can be maybe, let's say, a 3D image. So how do you kind of accommodate for that? You probably have to relearn the model to take care of that situation. Or sometimes, which is not, well, not sometimes, but like always, the customer preferences keep changing. So it will not probably adapt quickly to the customer preferences. One example of customer preference change that we have observed during pandemic was so before pandemic, people were not sort of well, people were still buying online, but I think the proclivity or the inclination to buy online actually increased. So that is like one way of thinking about it. And also the customer preferences vary based on specific shoppers. Like some are like we call it the spear phishing, where I know exactly what I want and I just go and I just buy because I have done my research before. Whereas in other cases, I'm probably like doing some kind of like window shopping where I'm just browsing. So again, my preferences will be different. The second method is what we'll be discussing here. It is the online learning. And one way of doing that is this bandit-based solution. And I'll describe what is bandit-based solution. That we will see that how we can mitigate this cold start problem through exploration. And also it can adapt to the ever-changing customer preferences. So in this slide, I will try to give a simple primer to this explore exploit algorithm. So explore exploit essentially is okay. Let me try to introduce you using a simplest possible model, which is a three-armed bandit. Imagine that each arm, so arm can be basically your options. Okay, let me step back a little bit. Why do we call it multi-arm bandit? Because this kind of algorithm was actually inspired by the slot machines that you typically find in a casino. And those slot machines are often known as the one-armed bandit. It's called bandit because it is trying to rob you of your money. But yeah, it's just a cultural way of calling those slot machines. So it's like, let's say you go to this casino and you have these three different slot machines and you do not know which slot machine has what kind of reward profile. Like if you pull the lever of, let's say, slot machine A, how lucky are you going to be to get the reward? You do not know that at the beginning. And each arm gives a reward when you pull it, but the catch is you do not know the true average reward. In this particular example, imagine that the true means or the true reward means are like I've given some quantification here, zero point 0.6, zero point 0.5, and zero point 0.3. But the algorithm cannot see these values. It has to learn through trial and error. To measure how well we are doing, we define a term called regret. Regret is simply the reward lost compared to an ideal oracle who always chooses the best arm. The formula here it captures the difference over the uppercase T rounds. It's fairly easy to kind of understand what I'm doing here. So here this mu star is basically the maximum that is coming from the oracle, which is zero point 0.6, the best arm, and RT is the reward that you're observing in the round T. And we basically just take a sum of that reward over the uppercase T rounds. And the delta between these two terms is called the regret. Um, now, because in the beginning, our estimates of each arm's rewards have very high uncertainty, statistically, the variance of the estimated mean drops as one over the number of the samples. So exploring more reduces the uncertainty, which leads to better decisions and lower regret over time. So that's why you have given here that this variance is proportional to 1 over ni. The subscript I is essentially the ith sample. So more exploration leads to lower variance, which leads to better estimates and hence lower regret. Now there are multiple ways of actually running the algorithm. The other known, so I'll be describing what is Thompson sampling here, but there's some other algorithms like the upper bound confidence, which I will not describe here. So what happens in Thompson sampling is that it is actually a Bayesian approach. Each arm has a posterior distribution over its possible reward. Early on, these distributions are broad and overlapping, as you can see in the first image. So sampling tends to explore. Later, the best arm's posterior becomes sharply picked and dominates the sampling process. So Thompson sampling also balances exploration and exploitation, but in a beautifully probabilistic way. This method relies on uncertainty as the key driver of intelligent decision making. And as you can see that after many pools, the posterior of the best arm, this is the red one in our case, so that is peaking, where the other ones, like the blue and the green ones, they are flattening. And Thompson sampling now draws higher sampling from the red curve as time progresses. So In the first phase, we call it where it does not know which one is best. So it's basically exploring, but as it starts pulling the arms more, it has a better idea. So at that point in time, it is exploiting, which is it's trying to pull the arm A more than the others. So this is Thompson sampling. This is generally speaking, it is a fairly well-known approach, and I would also say that it is predominantly used in many industry systems because it adapts well to the changing preferences and rewards, and you can also actually get rid of the cold start problem. Okay, so coming back to our problem of the reordering of the media contents. So let's say we have the algorithm decides to sort of try out different random orderings. So these are a couple of random orderings. And let's imagine a situation where the algorithm is trying to show the images that will get more clicks at the beginning. So these are the two different sort of samples that where it found that the number of clicks that these images are getting, and based on this, it then starts sort of exploiting. So you can see what we have done, and it's a very simplistic image, a simplistic example here. So the first image, which is the product with the white clean background, that is getting a total of 9 clicks. We basically just in this particular slide, I just added them. So here you can see 5 clicks, and here it is 4. So 5 plus 4, 9. We do the same calculation for the remaining, and this appears to be the more optimal ordering based on what we know about customer behavior. Now, the question, so this is trying to answer the first question, that how do we order them? And the second question is then, how do we evaluate the solution? And I guess that is probably the more interesting part, and we will dive right into it. Okay, so what is an experiment? So by the way, when I say experiment, I'm talking about the AB experiments or random control trial, RCTs. So let me take you a little back into the history. Like a long time back in the 1700s, a British ship's captain observed the less of scurvy among sailors serving on the naval ships of Mediterranean countries, where citrus fruit was part of their rations. He then gave half his crew limes, that is the treatment group essentially, while the other half, that is the control group, continued with their regular diet. The experiment was a success, showing that consuming limes prevented scurvy. Scurvy is gum disease, which is pretty common among the sailors. British sailors eventually were compelled to consume citrus fruit regularly. Now, let's motivate with another example, which is more close to us. So in the 1990s, an Amazon engineer created a prototype to show personalized recommendation based on items in the shopping cart. Internal reviews shared a contrary view that it may distract customers during checkout. A control experiment was undertaken, applying the new feature, and it won. So that is another example which is close to our industry, where experiments help us making a decision to build a feature or not to build a feature. Okay, so I'll start with maybe what is not a control experiment. The first one is a marketing campaign. So let's say we are sending emails to frequent shoppers, and we analyze the revenues from customers who opened the email, which is group 1, versus who did not open that email, which is group 2. Suppose group 1 bought more. Can we conclude if the campaign had positive effect on revenue? I'm actually looking for some answers here, just to make it fun. Although I'm trying to see if I can see the comments. Feel free to post some comments. I would like to see what you're thinking. Okay, no comments here. Anyways, let me give you the answer. So no, because the customers in group 1 may be interested in buying the product anyways. So we call it the selection bias. So this was not designed properly as a random controlled experiment. The second example, we call it the gift wrapping experiment. So let's say in US, we launched the gift wrapping feature using non-recyclable and recyclable material during September, October, and November, December timeframe respectively. We analyze the cells to determine the better policy. And suppose the cells were up during policy 2, which was during the November, December. So the same question, can we conclude that policy 2 served the customers better? So I'm just giving this a little bit of time to kind of understand the problem here. Okay, so this is also not a control experiment because in US, people typically buy gifts during November, December, which is the holiday season near Christmas, which leads to increased sales. So this is also a flawed experiment design because it did not capture seasonality. So the first one did not capture the selection bias, and the second one did not capture the seasonality. And hence, these two cases these two experiments are not controlled experiments. Okay, so next step, we will discuss some of the basic steps of designing an experiment. So first step is we have to state the objective of the study. Like in our media type example, do customers like images with product dimension information? The second step is we have to choose the response variable and define success criteria. Should correspond to the purpose of the study. In many of the experiments that industry typically runs in e-commerce, we typically go with something like the number of units sold or the number of products purchased. Then we choose the factors. So in this gift tracking example, it can be the control group perhaps is the non-recyclable wrap, and the treatment group is the recyclable wrap. So that is the factor where you want to differentiate. Then we choose our experiment design, which essentially is the like how do you want to split? You can randomly split the customers or the products. And then you start the experiment, you run it for a certain length of time, and you determine that length of time by doing some power calculation. Power is a statistical concept which tries to basically which tries to compute the probability that you will reject the hypothesis when it is not true. Then evaluate the experiment was essentially that is the part I will describe in more detail. But that is a statistical computation, and we try to answer this question: does it satisfy the success criterion? And finally, we make a go no go decision. That is, you want to make this feature or this product into the production. Okay, so coming back to this control experiment, let me give you a little bit more details here. So in a typical A/B test, the subjects and items are split randomly into control and multiple, and it can be one or more treatment groups. So control group is the group where the items or subjects of factor one provides you the baseline measurement, which is essentially often like the production model. And the treatment group is the group of items or subjects with the factor 2, which are experimented with features of interest, as I said, like the recyclable wrap. And on the right side, I show you this diagram where, let's say, the number of units sold is 15,000 in the control group, and the number of units sold in the other side is 20,000. And then you ask, like, which is better? Of course, like just by naively looking at it, it feels like the treatment is performing better, but there are some nuances to it. So let me also talk about randomization a little bit more. Randomization is the key difference of experiment study and observational study. In experiment study, when we design we design before the experiment, and sorry, sorry. So randomization attempts to balance the control and treatment group, and it makes sure that everything else is similar except the factor to experiment, and it reduces the influence of subjective bias in treatment assignments. So here you can see that I've given this little image that in our marketing email campaign, perhaps there are certain confounding factors like age and gender that is influencing the action, such as opening emails and also purchasing units. So we typically try to take those factors into account when you are when you're randomizing the customers. So as I said here, a better way to actually design that marketing campaign would be to evaluate the impact of email campaign to the customers. We randomly split the customers grouped by age and gender into control group. And that is where we are not sending emails, and the treatment group, where we send emails. And thereby we mitigate that selection bias because we are using age and gender for classification. Similarly, for the gift wrapping experiment, we randomly split products again by group by price and the product category. So product category can be like toys, books, etc. Into control group, where we apply the non-recyclable material, and the treatment group, where we apply the recyclable material. And again, this experiment is happening over the same time frame to avoid any seasonality bias. Okay, so what is the objective of treatment design? So in our particular real world scenario, we want to see if the customers like images with product dimension information. So that's what we want to learn. How to test it? So we will change the position of the dimension image. So what does it mean? So in the control, if a product is in control group, there will be no change in position. However, in the treatment, the dimension image is put first, as you can see in this particular visual. So in the evaluation, let's say in the first 2 weeks, the customers bought about 2,000 units from the control group, whereas on the treatment side, during the first 2 weeks, the customers bought like 2,050 units from the treatment group. So we can conclude that the customers bought more products from the treatment group, hence putting the dimension image in the first position has a positive impact of 0.25%. And we can launch this in production. However, there are multiple challenges when conducting experiments in industry and when we are trying to measure the effect. So most treatments introduce very small incremental changes. The relative change on the business metric known as the treatment effect is generally pretty small. As like, let's say we have given a number which we observe generally speaking, like less than 0.1% often. However, you might wonder like, then why bother if the effect is so small? Well, the small treatment effect can actually still have a huge impact. We have basically quoted some numbers from the Walmart's earnings call. In second quarter of this year, their revenue was close to $170 billion. So even if there is a 0.1% increase, that is equivalent to almost $170 million increase in the revenue. Now, since the effect is so small, the detection of such small change in business metric is challenging due to noise in the data. Because think about it, like we are actually trying to collect a sample of observations, and based on that, we are trying to estimate the population change. So that is where things can get a little challenging. So we need a precise estimator that can detect these small changes like this 0.1%, as I mentioned in this slide. Before we go into the more sophisticated methods, let me start with a very simple primer on this treatment effect estimation. So let's say we have this product group control with an average product purchase of beta naught. And in the treatment, it will be the beta naught plus beta 1. Essentially, this beta 1 is known as the treatment effect. We can estimate the beta 1 using some linear regression. And by the way, we are saying that this is the treatment effect because that is the incremental on top of beta naught. And beta 1 can be positive or negative. So the idea is that since the experiment is designed properly, taking care of the selection bias and the seasonality bias, these beta naughts will cancel each other out. And whatever is the remaining is the incremental, and that is what we try to estimate. So let's imagine that we have this very simple linear model for treatment effect estimation, where this y subscript I is the number of the purchase for the ith product. Then we have this beta naught plus beta 1, and this ti is a indicator variable, like a binary variable. It takes 1 when the ith product is in treatment and 0 when the same product is in control. And finally, the noise. So it's a very simple linear model. We run this regression to estimate the beta 1. That's what is that we are concerned with. However, there are two state-of-the-art methods for improving the precisions currently being used in the industry. The first one is where we use the pre-experiment variable in the linear regression. So what is that? So we say that, okay, let's say the experiment is starting today. So we want to include the last 2 weeks average units purchased for that particular product into the regression. which is, so that's what it is, XI stands for. We say that is the pre-experiment data for the ith product. The second approach is called the stratified regression. Essentially, we are dividing the products into smaller stratums based on the pre-experiment data. So imagine, let's say, a coffee maker example. So if the is a coffee maker example, if that is, it falls, let's say, on the top quintile of the products being sold in the last 2 weeks. So that will go in the fifth bucket. Imagine like there are like 5 buckets, and each bucket there is a group of products, and we just divide those products based on increasing number of units sold. And then we use some kind of linear regression inside those buckets or the stratum to estimate the treatment effect. And finally, we compute the weighted average of treatment effects across all the strata. So that is what we call the stratified regression. So the first one is we are introducing this pre-experiment variable, and the second one is having this bucketized or stratified regression approach. However, in our experience, we found after applying both these methods that we still have 80%, 85% of treatments with this low precision problem. And by the way, you can actually use both the methods on top of each other. Essentially, it means that you are introducing this pre-experiment data inside of each of those regression in the buckets. But still, we land up in this problem of low precision. So what can be done? Can we do anything better? So first, observed outcome. So we define these two terms. The first term is observed outcome, where what the customer sees based on the treatment assignment, and the counterfactual outcome, what the customer would see if the treatment assignment flipped. So we have given this table here, observed versus counterfactual, where on the rows where we have the control product and treatment product, on the columns we have this observed image ordering and the counterfactual image ordering. So for a control product, the customer will be seeing what is being created by the control model. And the counterfactual is what if the customer had seen this product under treatment, but that is counterfactual. That is we do not know. And similarly, for the treatment product is exactly the opposite. So a potential solution is that if the treatment has small incremental change, it does not impact many observations. But can you detect the observations with treatment impact? We can check if the observed and counterfactual image orderings are different. If the counterfactual and observed image orderings are different, we call it a trigger. And if they are same, we call it a non-trigger. Let me give you a simple visual example and to make things clear. So here on the left-hand side, we see that the image ordering did not change under both observed and the counterfactual orderings. So, and this is again, it depends on the customers. So for some customers, when visiting this coffee maker, there's no change in the image ordering between observed and counterfactual. And this happens because treatment does not change the image ordering. So we call it a non-trigger observation. Whereas on the other hand, if it was getting sort of swapped, if the images were getting swapped for other customers, then we will call this one as a trigger observation. And we will only take the trigger products or trigger observations into our calculation. Why so? Think of it with another analogy. Let's say we are designing maybe a clinical trial. So in a clinical trial, you are designing maybe a new medication, a new drug, and you want to see if the drug is actually effective. And you assign these drugs to two group of people, the control and the treatment. And let's also imagine that some people never took this drug. Then if we account for their outcome, then that will actually create more noise. So we only try to sort of concentrate or focus on that group of customer or that group of patients who are taking the drug in that clinical trial. So that is the same idea that we are basically bringing here, that if the algorithm is not changing the order, then don't bother. They basically will be just adding noise. So we will only focus on those where the algorithm is changing the order, that is the trigger ones. So now let's go into the little bit more deeper into the math here. So we said that in both control and treatment, we will have trigger and non-trigger observations. So the average product purchase, again, we define it as for the control non-trigger as beta naught. That is the average product purchase for non-trigger observations. Then the trigger control observations are different from non-trigger control observations. So beta 1 is this additional change in the purchase in this case. And finally, the purchase for the treatment trigger observations, which is the last row here, is different from the control trigger observations because the treatment actually displays a different output to the customer. Hence, customer response to the for the treatment trigger observation is the sum of beta naught, beta 1, and beta 2. Um, so we can bring all of them together in this slide. So I say that this not all product trigger equally. So and that is where the crux of the solution is. So the problem is detection of all trigger observation is pretty expensive, as we need to compute the counterfactual ranking for all observations. So imagine like in the best possible case, we want to know for each product if it was going to trigger or not for all the customers that are visiting that particular product's detail page. Now that will be really complex and complex and expensive because we typically have, let's say, products in millions, in tens of millions, and also customers can be also like even hundreds of millions. So if it is almost like a cross product, it will be a pretty large number, and it is computationally almost prohibitive to compute the trigger observations for every product customer combination that is possible. Um, so instead, what we are doing or trying to do here is something I'll explain. But first, I want to define what is a trigger intensity for the ith product, which is defined as the R superscript I. So in the denominator, you have the trigger observations, the sum of trigger and the non-trigger observations, and the numerator only has trigger observations. So this number will be a number, or this fraction will be a number between 0 and 1. And we write down our regression equation as the yi, which is the number of units purchased for that ith product, beta naught plus beta 1 r1, and then the beta 2 ri, and ti is that binary variable, and finally the error. And what we are interested in is the beta 2, because that is the treatment effect. So our rho, that is our average treatment effect, that will be the beta 2 times the expectation of Ri. It's an expectation, as you can imagine, because we are taking an average here. Um, and this bias and the variance of estimated treatment effect depends on the accuracy of Ri. So if you are very precise about measuring the Ri, it will give us better results, otherwise not. And we will show you in the next few slides like how accurate it can get. So um, in our paper, which I have also we have provided a link later, but in our paper we have shown some theoretical analysis of bias and variance. So two approaches. The first one is the full knowledge. Like if we had knowledge about all the trigger observations to compute the Ri that we consider as the full knowledge, and then the partial knowledge using a random number of samples to compute Ri. So the estimated treatment effect from the full knowledge is this rho hat, and the estimated treatment effect from the partial knowledge is rho hat tilde. So accuracy of Ri in the full knowledge case, that will be 100% accurate, and the treatment effect will be also unbiased. And the variance of the treatment effect will be proportional to the variance of the Ri. On the partial knowledge column, the accuracy will depend on the number of observations, and we will show how it varies. So let's say this number of observations is m, and we are trying to measure the bias. So the bias is the rho, the delta, or the difference between the rho and the expectation of the rho hat tilde. And that and the delta or the difference is proportional to 1 over m minus 1. And you will find all these proofs in the paper. And in terms of the variance, we see that there's an upward bias. Essentially, the variance of the rho hat tilde and the variance of the rho hat, it is proportional to 1 over m. So the key observation is that the partial knowledge has bias estimate, but the bias reduces linearly with the number of samples. Another question is how many samples are required to make this bias negligible? Um, so, so we found that the standard bias in the treatment effect reduces linearly with M, and bias reduces linearly, and detecting trigger status of a small number of samples between 10 to 70 is generally good enough. A much cheaper solution, when I say cheaper, like 10 to 100 times a cheaper solution, as the trigger status of a few observations are required. So you can see on the left-hand side in this graph, we are showing that this is the average treatment effect. If we had the full knowledge, it would have looked like this. On the partial knowledge, on the x-axis, we have the number of observations increasing. As it increases, the delta between this blue line and the orange dots, it keeps decreasing. It's like an asymptotic function, and it is reducing linearly with m. Similarly, on the right-hand side, we are showing the standard error of estimating this average treatment effect. On the x-axis, the same, the number of observations used to estimate the unit trigger rate, and the difference between the blue line and this orange dots, that is also decreasing. And we are calling it the upward bias because these orange dots are above the blue line, and this upward bias in the standard error is reducing linearly with m. And these graphs are based on the simulation of the theoretical result. Finally, time for some experiment results. So we compare our method of this partial knowledge, or using partial knowledge to precisely compute the treatment effect, and compare them with this state of the art. So we took results from real-life experiment platform used in industry. It's about 23 experiments, and in total about 147 treatments. We compared against the two methods, as we discussed earlier, the regression using the pre-experiment data as features and the stratified regression based on pre-experiment data. So we see that on the first row, the average standard error under regression is about 0.38. In stratification, it is 0.33, whereas in the partial knowledge, it is slightly lower. But the good thing to observe here is that the number of statistically significant treatments is actually increased under the partial knowledge. So in the regression and stratification, it was about 22 treatments that were statistically significant, whereas that number has actually it has it has increased by almost 1.5 times in under partial knowledge. And similarly, when we look for a more stricter condition of 95%, they are exactly same. Essentially, what we're trying to do here is, as you said, that we're trying to measure the effect more precisely. That means that we want to shrink the confidence interval. And if we are shrinking the confidence interval, that means we will get more statistically significant outcomes. And we want this number to be higher compared to this other two columns. So that is what we show. The partial knowledge method reduces the variance by 38%, and also the number of statistically significant treatment has increased by 145% using this the trigger intensity method. Also, we want to see the bias, if like our results are biased or not. So we see that we want to check if this is true in the experiments or not. So we see that the percentage of experiments where the 95% confidence intervals overlap. So imagine like you have the confidence interval coming from the, let's say this the SOTA methods, the regression and the stratification, and also from our the partial knowledge of the trigger intensity method. And the higher the overlap, we are more confident that these results are unbiased. So you can see that in almost every case in this first four cells, these numbers are close to 100%, which gives us more confidence that the bias is like negligible. And lastly, we also look into the percentage of treatments with the same sign for this average treatment effect. And we see that they are more than 70% times they have the same sign as AT. Now, you might wonder like, okay, why is this number so low compared to like the other four cells? That really doesn't matter as long as your confidence interval is almost the same. Because the point estimates can be slightly off. And since we're talking about like really tiny average treatment effect, it is possible that, maybe in the regression method, it was, let's say, 0.01% positive, whereas in our method, it is like negative 0.01. They're so close to each other. As long as the confidence intervals overlap by that significant number, we are generally feel pretty good about it. So ultimately, to conclude, no observable bias in the estimated treatment effect in experimental data, and our confidence interval of partial knowledge overlaps at least 99% of the times with the other two state-of-the-art methods. So to conclude, so we discussed a multi-arm bandit based real-world application in the shopping domain and the problem we discussed was about how to reorder the media types or the media contents in a product detail page. We proposed an A/B experiment evaluation method using sampled trigger observation methods. We also presented some theoretical results that shows that the bias of evaluation method reduces linearly with the number of samples used to detect the trigger rate for a product. And finally, we present the experiment evaluation results where we show that the proposed method reduces the variance by 38%. Okay, with that, I would like to conclude my talk. Time for questions, I guess. Please feel free to type your questions in the chat and I'd be happy to answer them.
Yes, participant, if you have any question, feel free to ask. Unmute yourself and you can ask the question, or you can write the question in the chat box also.
Dr. Sinha, actually, I have a question.
Sure.
Okay. First, let me ask the question. One question is there in the chat box written by Orchana. How much accuracy you get for real life use cases?
When you say accuracy, I suspect that you're looking for like the variance order, right? Um, So in reality, like in most industry A/B experiments, we do not reach the statistical significance because of, as I said, because of our changes are so incremental. Um, like probably I would say like we reach statistical significance like probably like less than 30% or so. But that is something that we're not surprised because we try to keep our changes as minimal as possible. Otherwise, it can create a shock, and that is generally not desirable. So, yeah, that would be my answer. Tanmay, if you want to add anything. Okay, cross the one
Okay,
was
Dr.
I think.
Sinha,
Yeah.
actually, yes, I have a question. As we all use Amazon shopping, Amazon for shopping, but we don't know actually the what is the main thing going in behind. So, though it is a very generic question, that what is the most impactful ways that AI is transforming the overall shopping experience?
Um, yeah, so there are many different ways, and I mean, you can if you're shopping in not only Amazon but in any other e-commerce website, you can see that they have now included some kind of conversational experience where you can like before people just used to like search by saying like maybe this coffee machine, etc., and you just hope to get the right product for your needs. But today you can actually give it a more natural language based question and you can be even more descriptive. Let's say an example that I'm thinking of, let's say you want to go camping somewhere and you know that this place is maybe where it rains a lot. So you can be more specific and you can just say that I'm looking for camping gear for a wet place, something like that. And given that this AI models, the LLMs, they have this world knowledge, they can actually kind of figure out that if let's say the camping gear is made of maybe I don't know, like some kind of water resistant material, they will be able to infer that that will be the right product for your need because you're going for a camping in a wet place. So that has been kind of a game changer because it is able to use this kind of a semantic deduction from the query and also from the product attributes. This is just one example of doing a search. Another example that I can give, again, it is now becoming fairly commonplace, is the product review summary. So at least I can speak for myself. If I'm, let's say, trying to purchase a baby product, I read the reviews from the other parents. And before I had to like scroll like a lot of times and just to understand like if this product matches my customer needs. But today I can just read the summary, which is just going over thousands of reviews from parents, and it tries to highlight both the good thing, the strengths of this product, and also some of the weaknesses. So that also saves me time. So these are a couple of examples where GenAI is being used not only in Amazon, but I would say pretty much in every other e-commerce websites or apps.
Yes, definitely. But means I also, when buying any product, I always look for the comments for 5 star and 1 star. Okay, to
Mhm.
get a comparison. But one thing to ask you, that how much trusted is these comments that which are given by the user? Means-
That's a good question. And generally speaking, there are different ways to measure trust. Again, like I do not work with that particular team so closely, but I can guess as a customer like what I look for when I am looking for more trusted reviews. Generally speaking, if someone is posting an image that is taken in their household or etc., that gives me more trust. If I see that this person has been a frequent shopper and also frequent review has been posting frequently reviews, or sometimes they have this kind of a like a badge that this purchase was verified. So all of these factors actually helps me to trust that specific review coming. Yeah, and then also like sometimes the review can be um, like some kind of spurious reviews, where whatever they're mentioning, maybe it's a one-off case, such as, for example, let's say, oh, this product arrived with broken packaging. Now, if that is not a common case, then I will just ignore it. So, yeah, you just apply your own judgment to some extent.
Okay, okay. Thank you so very much. There are a couple of questions in the chat box also, so I will read it out. First one is from Sanjeev Puri. He's asking, as if we can be third economy at earliest, how AI tool set enhanced to e-business intelligence model.
Um, I actually have some questions about the question itself. Um, what does it mean by or what do you mean by third economy?
It
I
means, I
think he
think,
means the third
third
largest
third
economy.
largest economy.
Oh, okay, okay, okay. Um, hmm. Well, I mean, it has been a transformative technology for many different reasons. Um, I'm just trying to think like how to kind of best answer it. One thing that I can think of is, especially in the Indian context, is that India is a land of multiple different cultures and languages. And in the past, I have known because I've attended some talks from like Flipkart, where they have really struggled in inferring some of these language issues because we often converse in a mixture of languages. Like I know, for example, in Calcutta, people talk like in the same sentence we use English, Bengali, Hindi. And we expect these search queries that the search engines inside this e-commerce websites or apps, they should be able to understand us. And it had been a challenge. And I believe that with the presence of world knowledge, LLMs can actually effectively solve this problem, because I have actually tried playing with ChatGPT, where I actually ask ChatGPT to produce something in Benglish, which is like a combination of Bengali and English, and it does it perfectly. So that is like just one sort of simple use case where GenAI can actually help us. Um, and of course, like this is more customer facing, but also for the builders, like who are actually the software engineers who are actually building these products. It has been quite a game changer for them. It has very much increased the productivity, especially on the operational side of things, where let's say whenever like any kind of like system tickets gets generated or maybe customer issues are getting reported. Earlier, it used to take a long time to like triage because you have to like manually go over the context and understand them. So GenAI has been really helpful in kind of doing that triaging automatically for us. So these are like a couple of examples, both customer facing and sort of more productivity enhancing benefits that you're observing in pretty much any industry, but is more specific to the e-commerce. Okay. The second question is, can you please suggest some project research topics which can be tried in academic setup? Tanmay, you want to answer that question if you have ideas?
Yeah, sure. Like, I mean, yeah, we are working on multiple projects where, like, some research, I mean, some new research would certainly help us. So, yeah, something like whatever we are doing, as Arnab showed in these slides, regarding this media content ranking. And yeah, like currently people are exploring, I mean, there are already some existing methods for doing that, using learning to rank, using some type of neural networks, but people are also exploring some GNAI approaches to rank the media content or any type of content. So yeah, like, yeah, if you are interested, then maybe we can explore that area.
वो बोल रहे थे उसके मैंने सुना वो आज वो लाइव हो वो बताई थी उसकी मैंने 11 तारीख को ही वो
Sorry, I
हफ्ते
have to interrupt you.
Sorry.
You are
Yeah.
barely audible. Um, Professor Bandhavada, if you were able to hear the
Yes,
question
yes,
clearly,
yes, yes.
yeah.
Next question. Next question is from Priyanka Das. Uh, Good evening, all. I have a question that why is shopping experience considered an important variable in retail analytics?
Yeah, I can totally answer that. Imagine, you know, okay, maybe I turn this question around, like, which websites do you shop from? If I were to guess, again, I'm just speaking for yourself. I do not know you, but if I were to guess, like the usual suspects would be perhaps like Flipkart in India, perhaps Amazon, perhaps I don't know what else is popular in India. But it should be a hand. It should be like you can just count them in your hand. But I'm sure there are like so many other options available out there. So why do you shop in those handful of websites? Um, and I guess the experience here means that you trust the price that they are being charged, the fair price. You should be getting it quickly, and also the ability to return, like the basic things that we come to expect as customers. And when I say the experience matters, because like there are certain websites where you go and you have this feeling like, oh, I do not know if I can trust this information, or you feel like, oh, I'm so overwhelmed with so much of information. Whereas in some other nicely curated, crafted websites or apps, you feel like I have all the right information that I need to know, and you just go ahead and order. So we have seen that if you can create trust with the optimal amount of information, that reduces the friction of making a purchase decision, making up your mind, and that ultimately leads to more volume, more purchases. So it matters, especially if the website is like one simple example. If let's say you're ordering from phone and your app is taking maybe a couple of seconds to load versus an app which just opens right away, which one are you going to be likely to be using in future? I suspect the one that has lower latency, because you don't want to wait, and that gives you a feel like, oh, this website or this app is kind of slow or broken, etc. So those things, those tiny little things actually matter. And similarly on the UX side, like sometimes, where if it is just overwhelmingly sort of cluttered with information and you are struggling to find, let's say, what is the return window, then you do not earn trust, or the app does not earn your trust. So there's some of the examples where the experience actually points you to shop more or less, if that answers your question.
Thank you. Next question is from Kaliavani. Nowadays, we have a lot of AI tools. How can we predict which one is best?
It's a difficult question, really, because the landscape is changing so rapidly. And why I say this, because very recently the Gemini 3 is released, and it beats pretty much all other models in terms of the standard benchmarks. So it is like whatever I answer today, it will be wrong in the next month probably, or maybe in few weeks. So I would just say, like, start using any one. And the good news is that, like, it's not about just the tool, but it is also the context that these tools have, and also for the kind of need that you have. Like, to begin with, let's say, like, I use ChatGPT for different things, and I like its results. But for my professional work, I use some internal tools that we have within Amazon. And these things are also not static, they're changing, and I use different tools for different reasons. So start using one of them. The more context, the more you play with it, the more context the tool will have about you, and it will remember certain things about you. And ultimately, that will be a much better agent about you, because it knows more about you than, let's say, another random. Like, maybe it's better in terms of beating benchmarks, but it does not have enough context about you. So start using any one of them, and it should be fine. But that is more from like, let's say, the regular day-to-day usage. But if you want to use, let's say, LLMs for your research or something else, um, you have to be careful. Like, for example, what we are learning is that it's not always the case that you need a large language model. Sometimes actually small language models can do the job perfectly. So if so, you have to understand, like, what is the problem that you're looking to solve. If that problem can be solved using maybe a very simple classifier, you probably don't need something like a GPT-5 kind of model. So it's a trade-off that you have to make.
Okay, next question is from Ajitesh Ghosh. Which is the role of the business rejection rate to calculate the best model?
Okay. I suspect you're talking, or you're asking about the the statistical concept of uh, rejecting the alternate hypothesis. Is that right? Okay. Okay.
Yes.
Yeah. So whenever we are running an experiment, we are essentially doing an hypothesis testing. The null hypothesis is that the new model will perform no better or no worse than the production model. And then we run the experiment, and then we typically, if the result is statistically significant, that essentially means that we are rejecting the null hypothesis, because our p-value is so low, or something like that. Now, it is important in the business case because we don't want to change the experience just for the sake of it. Um, I mean, in some cases, we probably want to do that. For example, let's say if you want to fix a bug, maybe it's a bug in the UX that you want to fix, and you're running an experiment, even though results are no worse or no better than the production, we feel that is the right thing to do anyways. So in that case, regardless, we'll launch it. But in other cases where maybe you're thinking of, like, this reordering example, whether it makes sense to show dimension image at the beginning, there it is probably important to not start the pot, or to not to mess with what is already working perfectly fine. And we might just say that we won't launch unless it is statistically significantly better compared to the production model. So yeah, to answer your question in one sentence, it depends on the situation, but it is definitely important to the business.
Okay, next question is from Navneet Kaur. Actually, Navneet Kaur has a couple of questions. The first one is that how can we coexist with machines that inherently lack human values?
That's an interesting philosophical question. But I would actually like to disagree with that premise, because if I think about these models, I mean, specifically these large language models, these are trained with large corpus of available information. So the human values are kind of embedded into these things. So yeah, but it's probably a very philosophical question, and I don't think I'm qualified to kind of talk about, let's say, ethics or even like the biases that we have in the human generated corpuses that are available. But I don't know how to answer this question, essentially.
Okay, the next question is again from Navneet Kaur, that what happens when a program that can rewrite its own code diverges from the intention of its creator to achieve its goals?
Okay. Um, Generally speaking, again, like if I want to sort of look into my own experience working in industry, if that happens, we reject that code essentially. Like we have guardrails to prevent that thing from happening. In fact, there are tools that are being developed that starts from like the design spec. So we kind of, yeah, there are tools that are already publicly available. For example, in AWS, they have a new tool that called Kiro, where it starts with the design spec, and then it'll work from the spec, it'll do the design work, then it'll define the APIs, and then it'll go and write the code for you. And it'll also write the test cases and everything else. So in reality, I mean, of course, you can imagine a matrix-like situation, but that is like fiction. But in reality, there are strong guardrails to prevent that from happening. Um, if that answers your question.
Next question is from Archana. How to decide optimum number of samples for specific use cases?
Salma, you want to take that?
Yeah, sure. So I'm guessing like the question is regarding the optimum number of samples for that trigger intensity method. So yeah, I mean, it's kind of like we don't have a theoretical sample complexity analysis here, so which can say that what is the optimum number of samples. But as we did some like bias variance analysis, and based on that we get some bound on the bias, and with that bound we know that at least the number of samples required is somewhat linear, or actually linear. So we did some simulation study to determine, okay, how the number of samples are decreasing the bias, and based on that we came up with that number of, something like samples within the range of 10 to 70. And we also saw that in our experiments, like those many number of samples are good enough. Like in our experiments, we generally collect something around like at least uh, 20 to, like, yeah, I guess 20 to 60 samples for a product. So that many number of samples were good enough to get a very good results. So yeah, so to summarize, I would say like there is no like a theoretical equation that we can use or that we have developed to know what is the right number of samples. As based on our simulation and experimental result, we saw that it is somewhere around 10 to 70.
Okay, I think there is no more question. If you are having any other question, you can ask. Okay, I think there is no more question. Okay, Dr. Sinha and Dr. Das, thank you for the enriching and enlightening talk, and the number of questions itself speaks that the session was really engaging and interesting. And thank you very much for your time and support on behalf of the whole organizing team. I thank you and have a good day.
Thank you for having us. Have a good time. Bye.
Yeah.
Bye.
Thanks.
Bye.
Bye.
Bye. Thank you, participants. And tomorrow we will again meet at 5:45 p.m. Good night.